Hello, and welcome back to the web series Developing Spectre using Innoslate's digital thread. My name is Mallory Jones, and I'm a systems engineer here at Spec Innovations. In the previous videos, I introduced the Break the Ice Challenge, initiated the Lunar Rover project, and demonstrated Task 1 and Task 2. In this 7th video of the web series, I will demonstrate the work conducted during Task 3 of the Lunar Rover project. This task was crucial for testing the rover system to verify and validate the Spectre lunar rover prototype. To complete Task 3, test the lunar rover prototype, Innoslate's Test Center and integrated tool ANSYS were utilized throughout the following processes demonstrated in this web series video. In the Systems Engineering V model, this work took place during integration and test, operations test and evaluation, and transition. The Task 3 statement of work was broken down into several subtasks: create verification and validation requirements and test cases, simulate the lunar environment, test the Spectre rover prototype, conduct performance and environmental analysis, and incorporate Innoslate's digital thread. From this task, a final report document was produced, and the Spectre rover prototype was productized. To begin verification and validation of the Spectre rover prototype, test suites were created in Innoslate's Test Center. These test suites hold test cases for testing the rover prototype and each of its components. The goal of this testing was to verify the rover's functionality operates properly and as expected. Once the test cases were drafted, they were traced back to their corresponding requirement for complete end-to-end traceability. The test suites were created to verify the various aspects of Spectre, including the robotic arm and servo motor, the LEO rover prototype, and the assembled Spectre prototype. The excavator claw design was verified using ANSYS tools. This will be demonstrated in the next video. In Innoslate, these test suites were created by going to the Test Center, selecting a new test suite, and creating test cases one by one. This process is similar to recording requirements and document. These test cases each held a test procedure and the expected results of the test procedure. A verified by relationship was then added to trace the test case back to the verification requirement. This allowed for easy tracking of the complete verification testing. The Robotic Arm Verification test suite was created to verify the robotic arm and its servo motors met their defined functionality. This included steady power supply from an external battery, proper operation of 6 different servo motors, wireless communication via a remote control. 10 of the 12 test cases passed in the Robotic Arm Verification test suite. The 2 failed test cases involved a systematic overheating issue with the servo motor. Once the testing was complete, the actual results were entered in each test case, and the status was set to pass or fail. To resolve this issue and prevent it from occurring each use, a buck converter was added to drop the voltage received by the servo motor. The internally programmed voltage limits were also adjusted. These resolutions successfully prevented the servo motor from overheating during future use. The LEO rover verification test suite was based off of the LEO rover's manufacturer documentation and specifications. These test cases were created to verify the rover body met its defined functionality. This included proper power on and off sequencing, maximum and average speed, maximum payload capacity, battery operational runtime, clear camera visuals, and wireless communication via a user interface. 17 of the 20 test cases passed in the LEO rover prototype verification test suite. The 3 failed test cases involved the maximum speed tests. Since modifications and additional equipment were added to the LEO rover prototype, it was unable to reach its manufacturer maximum speed of 0.4 meters per second. The Spectre verification test suite was created to test the actual functionality of the fully assembled rover prototype. These test cases were used to verify Spectre meets the expected functionality requirements written during Task 1. This included functionality such as battery operational runtime, battery charge time, LiDAR obstacle detection, maximum storage capacity, storage container durability, maximum excavator claw load capacity, time to load and unload materials, dual suspension, average velocity with and without carrying the maximum load capacity, and average velocity at an incline with and without carrying the maximum load capacity. 28 of the 30 test cases passed in the final Spectre Rover prototype verification test suite. The 2 failed test cases involved the incline velocity tests. The Spectre Rover prototype was unable to drive at its average speed up a 30-degree incline with and without carrying a maximum load in the storage unit. After creating the verification test cases and relating them back to their verification requirements, a traceability matrix was opened to confirm each Spectre Rover verification requirement was verified by a verification test case. In Innoslate, this was done by navigating to the verification requirements document and opening a traceability matrix. In the traceability matrix, the related option was selected from the X-axis drop-down menu and the verified by relationship chosen as the relationship type. This process automatically checked each requirement for a verified by relationship to a test case. By scanning across the X's in the rows of the traceability matrix, it was confirmed that each requirement is verified by a test case. After completing the verification of Spectre Rover prototype and its subsystems, test plans were created to begin the validation of Spectre. Validation tests were created to judge the prototype's actual functionality against its expectations and the mission requirements defined by the Break the Ice challenge. Test cases were created to test functionalities such as speeds and travel times between the scaled-down lunar rover sites, regolith excavation and offloading rates, storage and protection of collected materials, and equipment protection against environmental conditions. In order to best replicate the environmental conditions on the surface of the Moon, validation testing was completed at a local sandpit. 14 of the 16 test cases passed in the Spectre Rover prototype validation test suite. The 2 failed test cases involved the collection of the material that was chosen to replicate frozen water on the lunar surface. This selected material is too dense for the excavator claw to be able to pick up, causing the water load and unloading collection tests to fail. Up next on the web series Developing Spectre using Innoslate's digital thread is a video demonstrating Innoslate's integrations. Thank you again for being here today, and I'll see you in the next video.